Hello students, welcome to Om Institute and welcome to the next video on the Engineering Services 2025 Prelims examination. And in this video, I'm going to talk about the solutions of control systems. Okay, questions both in EE and EC, that is ENT, Electronics and Telecommunication paper, because control systems was on a very easier level for both the papers you are going to see. Okay, so I'm combining the questions and discussing in this particular video. Right, so let's get started and yeah, here it is. If you have appeared in the ESE 2025 prelims, you can match your answer key, or if you're preparing for upcoming, see the reason I combined it also, like there will be many aspirants who are just preparing for next ESE, next GATE or ISRO examination. So all these can be a good practice questions in that sense as well. Okay, but the moderate the paper is actually very easy. I'll not call it as moderate also for control system. Okay, so I'll start first with the ENT questions. Okay, first I'll start with the ENT questions. So yeah, here it is. The closed loop the control system has the characteristic equation given, and as per the Routh-Hurwitz criteria, the system is what? Okay, so it's cubic equation. See, you can feed into Routh-Array, or what you can clearly observe that the inner term BC, okay, and the product of outer term, this is what I call it as AD. Okay, this is 1.5, this is 4.5 into 3.5. So very clearly BC is greater than AD. So hence stable has to be there. System has to be stable. That is what correct. Now that is what you really know about the cubic equation. Now next question. So answer is stable. Option number A. Okay. Next one is which of the following is an effect of phase lead network? Okay. So phase margin is decreased. No, phase lead in fact will increase the phase of the system, eventually increasing the phase margin. Okay, so this is wrong. The phase margin is increased. Okay, bandwidth is also increased. It actually shifts the omega g to a higher point. It acts as a high pass filter. Okay, so bandwidth is also increased. Velocity error is decreased. Velocity constant is usually decreased. Again, no. Okay, again, no. It is usually increased. Okay, the slope of the magnitude curve is reduced at the gain crossover frequency. Like I told you, okay, see, if it is a phase lead network, okay, this slope, to be honest, is actually in terms of the absolute slope, I would say, because if I talk about the lead network, this is how the lead compensator will look like. Okay, and let's say if this is some original Bode plot, okay, so this lead, because it's a positive magnitude case, how the slope will be affected? If this was the original slope, after a particular point, it's going to deviate this way. Okay, so if you talk in terms of value, it usually increases, but in terms of magnitude of the slope, okay, the magnitude of the slope, it is reduced. Okay, so the slope of the magnitude curve is reduced near the gain crossover frequency with the relative stability improves. Okay, so this is what can be taken as the correct option here. Okay. Option number D. For the first order system with the input ramp function, what is the steady state error? Okay, what is the steady state error? You know, if you have gone through your notes, this is a direct answer that you should have, because what you know about the first order system, the transfer function is 1 upon 1 plus st. And what is the steady state error for the ramp function? Okay, the ramp function. Okay, so the input that you apply is ramp, and ramp is 1 by s square. Okay, and then the steady state error will be the error between the input and output. Okay, so what is the input? 1 by s square. Output will be 1 by s square into 1 plus st. Okay, limit of s tending to 0, s into the error signal. This is what is going to be the error signal. Okay, so you can simplify the terms. This becomes limit of s tending to 0, 1 by s. I took s square outside. Then what is left in front of you? 1 plus st minus 1. Okay, that is only st divided by 1 plus st. S cancelled, put s tending to 0. Okay, t upon 1 plus 0. That is what I call it as t. It should be there in your notes directly. Okay, if you have studied first order systems. Okay, next question. Second order system has the transfer function given to you, 25 upon s square plus 8s plus 25. If the system initially at rest is subjected to unit step input at t equal to 0, okay, the second peak in the response will occur at what time? Okay, so the time for peak is generally given by the formula n pi by omega d, where n is odd integer. Okay, the first peak, which is also known as the maximum peak, occurs at the n equal to 1, that is pi by omega d. Okay, that you call it as the peak time. So if you talk about the second peak, the time will be the second odd value. Okay, the n can be odd, means the second odd value will be 3 pi by omega d, or further omega d is written by the formula omega n under root of 1 minus zeta square. So this becomes 3 pi upon omega n. So what is the omega n? Omega n square is 25. So omega n would be 5. And then this factor 2 zeta omega n 5 is 8. So how much is the zeta? 8 by 10, that is 0.8. Okay, that is 0.8. So omega n is 5 under root of 1 minus 0.8 square. So this becomes 3 pi upon 5 under root 1 minus 0.8 square is 0.6. 5 into 0.63, 3 and 3 cancel. The answer has to be pi. Option number A. Option number A, answer is pi. Next question. Which of the following is not the correct advantage of frequency domain analysis? Okay, let's read. Frequency response tests are simple to perform. Okay, correct. We need to see which is the not correct. So yeah, usually the frequency response tests as compared to the time domain computations are simpler, easier. Those systems which do not have rational transfer function, the frequency response can precisely be applied to them also. Yes, because even if there is some irrational, we can split it into see what is there in the frequency response. You can represent any frequency spectrum by two parts, magnitude spectrum and phase spectrum. Okay, so whether it is rational or irrational function, we can calculate magnitude and phase spectrum to that particular part as well. Transfer function can be obtained from the frequency response of the system. See, so say one of the important frequency response domain parameter, say Bode plot. Can you obtain the transfer function from the Bode plots? Okay, right. Yes. Okay. Frequency response methods can be applied for non-linear systems. No. Okay. All this, transfer function or frequency response theory that comes up, with the help of convolution properties. Convolutions we know are applicable for LTI systems. So hence, frequency response methods cannot be applied for non-linear system. Okay. So D is the not correct answer. We have to choose the not correct answer. We have to choose the not correct answer. Okay. So we'll choose it at D. Consider the following statements again. Okay, so there are some basic understanding question. The Nyquist criteria provide the theoretical basis for using the loop frequency response to determine the stability. Yes, of course, the Nyquist criteria will use the loop frequency response. Okay, that is the GSHS or GJ omega HJ omega, but it is used to finally determine the stability of the closed loop system. Okay, so this statement is correct. It may be used to assess the stability from experimental data describing the system. No, I mean, no, because, to describing the system, assess the stability. See, from Nyquist, okay, how do you talk about stability? The stability criteria is simply given by n equal to p plus minus z plus or z plus minus p plus, depends on the contour taken, the direction of the contour taken. Okay, so, what you actually need to assess the stability is actually the Nyquist plot itself, so that you can notice the encirclements from the plot. We don't need any experimental data. We need the complete plot of the Nyquist one. Okay, so this, and even if some data, what type of data they have not clearly mentioned. So this is definitely some not correct statement only. So which of the above statement is or are correct? I will choose option number A. I will choose it as option number A, one only. Correct. Next question. So yeah, following statements again. Now this is with respect to Bode plot. It is a method for studying the stability 100%. Okay, stability of linear feedback system. Second, it is useful in developing engineering intuition regarding the effect of pole zero placement on the frequency response. See, yes, that's the reason. See, when you talk about any phase lead, phase lag compensator, any compensator which places the pole and zero, how do you study even them? Okay, the basic study, the basic effect of lead lag compensator also we do with respect to frequency domain analysis in terms of Bode plot. Yeah, because when you look into Bode plot, you can clearly mark the poles and zeros, by the change in corner frequency, and also this is also a correct method only, correct statement only. So here both 1 and 2 are correct. Okay, which of the above statement is or are correct? Both 1 and 2. So there is a characteristic equation given. Okay, what is the loop transfer function? So how do you generally arrange the characteristic equation? 1 plus GSHS equal to 0, GSHS being having that gain factor K, or we can write it like this. Okay, GSHS may be arranged this way, 1 plus K n by D. So what you can do, the given characteristic equation, divide by this particular term. Oh, sorry, I'll first open with K. I have to separate out K. So I can write this way, S square plus 2S plus SK plus 4K. So if I take K common, k, it is s, and here it is going to be 4. This is equal to 0. Now divide by s square plus 2s. So you get 1 plus k s plus 4 upon s square plus 2s, that is s plus 2, and this is equal to 0. This much should be the answer. Okay, so what is the loop transfer function? K s plus 4 upon s plus 2. What is there? Basic question. Option number B. Which of the following is not the correct property of signal flow graph? See, very basic understanding questions they have put up. Okay, so the signal flow graph is applicable to non-linear. See here itself, signal flow graphs can only be, the graphs can only be drawn for linear. Although block diagrams may be drawn for non-linear, but graph, okay, can only be drawn. The signal flow graphs can be drawn for linear. So this statement itself is not the correct one. So option number A itself is right. Okay. Rest you can read and understand. Okay, rest will be correct only one option we can mark. The value of the variable at each node is equal to the algebraic sum of the signals entering that node. Correct. This is how we read and write down the equations from graph. The signal gets multiplied by branch gain when it travels. 100% correct. Okay, that is how you take the output of the branch. Okay, the signal flow graph is not the unique property of the system. Yes, very correct, because for a single system you can draw the graphs in multiple ways. Correct. So okay. Now, the electrical engineering questions. See, for the E&T, I'll specify that, I've mentioned a numbering of the question, but that is in accordance with the set T, the set C. The numbers could vary in different set. Okay, but question remains to be same. Now, looking into these control systems questions for electrical. So, see, many of the questions were theoretical in EC and one or two basic calculative question. Okay, right. So, for the type 2 system with the unit ramp input, okay, type 2 unit ramp input steady state error 0, because type 2 will give a finite error. Okay, type 2 na, okay, if you talk about step also, the error will be 0. If you talk about ramp also, error will be 0. Only for unit parabolic it will give you a finite non-zero error, and that is given by 1 upon Ka. Correct. Answer is 0, straightforward. In fact, in electrical paper they discussed a lot many questions around error only. Okay, see another one. For a unity feedback control system, the forward path transfer function is given to you. Okay, the positional and velocity error coefficient. Okay, what is this? Type 0, na? Type 0. Okay, there are two poles, but none of them is origin. Okay, number of poles of GS at origin when the system is in unity feedback is the type. Okay, positional error coefficient. What is the positional error coefficient? Kp is limit of s tending to 0 GS. Okay, so 10, just s tending to 0, you will put 10 upon 1 into 5. So this is equal to 2 only. Okay, this is equal to 2. Then what is the velocity error coefficient? Okay, it is given by limit of s tending to 0 s into GS. Okay, so there is no pole at origin to cancel s. Okay, so s into GS, s will be multiplied here. Directly s tending to 0, numerator 0, denominator non-zero, so answer will be 0 only. So 2 and 0 respectively, option number B it has to be. Option number B it has to be. Correct now? Okay, next question. The steady state errors for type 1, type 2 and type 3 systems, okay, with parabolic input, okay, with parabolic input, okay, and type 1, type 2, type 3. So, parabolic, see, if you talk about type 1, okay, the error will be infinite, okay, because parabolic, with type 1, ramp will give the finite error, parabolic is higher order, it will give infinite error. For type 2, as I just told you in the previous question itself, okay, the error, okay, due to parabolic input will be finite, given by 1 upon Ka. Okay, and for type 3, cubic will give you the finite error. Okay, but any lower order input like parabolic, ramp or step will give the 0 error. Okay, so it has to be infinite and some constant and 0. So option number A. Option number A, infinite and some constant value and some 0. Okay, this has to be the sequence. Simple one, na? Okay, next. Okay, next. If any root of the characteristic equation has positive real part, or if there is a repeated root on the j omega axis, the system is unstable. What is there? Any root with positive real part means RHP. Okay, and both of the conditions you know. Okay, RHP also you can directly say unstable, but yes, we also know that if there is a repeated root on the j omega axis, okay, in time domain it corresponds to the function of the kind. Okay, it corresponds. See, root with a positive real part corresponds to the function of the increasing exponential e power at. Okay, right. So linearly exponentially increasing function. Okay, but Repeated root on the j omega axis will give the rise to the function of the kind t into sin t or t into cos t. Okay, so at t tending to infinity, this and this both will be unbounded. Output will be unbounded. Okay, so yeah, unstable. Next question. Consider the unity feedback system GS equal to 1 upon s plus 1 square. What is the phase margin? Okay, basic calculation only. Phase margin is calculated at gain crossover frequency 180 plus angle GJ omega C. Okay, GJ omega G. Okay, angle GJ omega G. Okay, now what is the but what is omega G at which the magnitude is 1? So if you convert to the frequency domain, this becomes 1 upon 1 plus j omega whole square. Correct. So what is the modulus of j omega? What is the modulus of j omega? 1 upon 1 plus omega square. Under root and square cancel. The 1 upon 1 plus omega square, this has to be 1. At omega G, this has to be 1. Mod GJ omega G is 1. So solving from here, okay, what is omega G? 1 plus omega G square is 1. 1 cancel, so omega G square 0, omega G equal to 0. Okay, then what is the angle expression? 180 plus angle expression of this numerator is positive real number, so 0, denominator minus 2 because it's repeated factor, minus 2 tan inverse omega. At which point I need omega G. Okay, but omega G is how much? Omega G is 0, tan inverse 0 is 0. Okay, so 180 minus 0, 180. It has to be option number D. Very basic calculations only. So it is option number D, 180 degree. Correct? Okay. Next question then. For the system having the open loop transfer function GSHS equal to K upon S, S plus 2, S plus 3, what is the breakaway point? Okay, what is the breakaway point? See, we can solve it, but first tell me where the breakaway point is going to be. Just a rough intuition. Okay, so the poles, the open loop poles, one is at origin, one is at minus 2, one is at minus 3. Okay, so one root locus branch will start from minus 2, one root locus branch start from origin. Both will be approaching each other. They will collide somewhere, and that is what is going to be breakaway point. After this, this is how the root locus will complete. One branch will start from minus 3 and it will travel to the negative real axis based on the direction of asymptote. This is how the root locus will actually look like. The question is this breakaway point. You don't have to draw the root locus, but question is this breakaway point. Okay, which has to be between 0 and minus 2. Okay, so there are multiple options between 0 and minus 2. So how are you going to calculate? First, write down. Okay, if you take up the characteristic equation, 1 plus GSHS equal to 0. And from the characteristic equation, write down K as a function of S. Okay, so if you write down K as a function of S, it becomes minus of S, S plus 2, S plus 3. Can be written as minus of S cube plus, how much it becomes? 2 plus 3, 5, S square plus 3 into 2, 6S. Correct. So then I will solve dk by ds equal to 0. dk by ds becomes minus of 3s square plus 10s plus 6 equal to 0. Correct. 3s square plus 10s plus 6 equal to 0. Okay. So on solving this, s should be minus 10 plus minus root over b square, that is 100, minus 4ac. So 4ac will become 24 divided by 2 into 3. So yes, s is minus 10 plus minus under root of 76 divided by 6. Okay, so under root of 76, take a guess, 9. It's closer to 9, approximately you have to match. So minus 10 plus 9, minus 1 by 6, one possibility. Okay, minus 1 by 6. And then minus 10 minus 9, minus 19 by 6. Okay, so that's going to be definitely not the case. So minus 1 by 6. Okay, let me check the calculations. Oh, I think, yeah, this calculation has gone wrong because otherwise options are not matching. Sorry, my b square minus 4ac. So 4ac here is 72 actually. I forgot to multiply it by 3. 4ac. Correct. Now it is 72. So only under root of what is left here is under root of 28. Under root of 28. Okay. So which now you can approximately guess as 5. Okay. We have to just match the option now. Okay, so minus 10 plus 5, okay, minus 5 by 6. Minus 5 by 6 is minus 0.83. Okay, and the other one will be minus 10 minus 5, which is minus 15 by 6. Minus 15 by 6 is minus 2.5. It has to be between 0 and minus 2. Okay, it has to be between 0 and minus 2. So then option number B, Okay, point close 3, 0.83, closer one is 0.785. Okay, so option number B. Option number B is going to match. Correct? Option number B. Next question then. Right? A mathematical abstraction to represent or model the dynamics of a system utilize three types of variables called as what? Okay, called as what? Okay, so now you can just look into the options and decide what do you need, okay, to study, okay, or to represent any system. Okay, the input, the output, and the internal state of the system, which is represented by the knowledge of state variables. By the knowledge of the state variables. Correct? Okay, this is what it is. Okay, to explain the complete dynamics of the system. Okay, next, what input you applied, how the state is modified, and what is the final output you get. If it is possible possible to transfer the state from any initial state xt naught to any other desired state xtf in specified time by a control vector ut, then the system. See, even in ESE, it's not like the paper is always so easy. This time control system has been very easy because in ESE they have even asked the questions based on controllability, based on Kalman's test or Gilbert's test, or the questions on observability. But this is just a definition. If it is possible to transfer from any initial state to any desired state by the application of the input vector, control vector, then the system is said to be state controllable. Definition, just definition they have asked. And look into one more. Okay, if every state xt naught can be completely identified by the measurement of the output over a finite time interval, then the system is what? Okay, then the system is what? Yes, if you are able to observe every state, identified means observe by the measurement of the output, then the system is said to be completely observable. Correct? That's it. Definitions of state controllability and observability they have discussed. That's it. Finished. These are what were the questions. So see, very fundamental. Again, I'll repeat, but control system sometimes can bring decent questions. Like, before the ESE exam, I've taken some sessions on PYQs of control systems also, signal system also. So there you have seen some good questions. But this year, not only control system, even I have brought to the questions of signals also. They were pretty easy. In fact, maths and aptitude also, I made a video pretty easy. Okay, so more or less these subjects like signals, control have been really very easy and very achievable, and some of the questions are theoretical. And for that reason, it is also important to go through your notes thoroughly, because if many questions are theoretical, you should be very clear with the concept, because it looks easy, but I have seen that many students, especially with this true or false questions, they little bit struggle. So that should not happen. Okay, and that you can only secure by comforting your notes, and at the same time, problem practice of course will help you, will give you more and more accuracy and sharpness in your problems. But yeah, for any exam like ESE especially, thorough understanding, thorough revision of notes, I would say, is very important. Okay, so thank you. And yes, as I told you, even if you are a future aspirant of ESE, GATE, ISRO, any exam, these basic questions, you can take this session as a basic question practice for you. Okay, thank you, stay safe and take care of yourself.